Let me ask you a question, and I want you to be totally honest with me. Have you ever walked out of a Cambridge computer science exam, specifically that notorious 9618 paper, feeling absolutely brilliant? Like, you know you crushed it, but then weeks later, you get your paper back and realize you dropped incredibly easy marks on an Xor gate question. You literally knew the logic, you memorized the gate, but the examiner's red pen just slashed right through your answer anyway. Look, I know that feeling, and it is honestly one of the most frustrating things in the world. But today we are changing that narrative entirely. In this explainer, we're talking about making your mark on these exams. We're talking about bold strokes of analytical creativity, but absolutely backing it up with the solid, impenetrable structure that Cambridge examiners actually demand. The truth is most students lose completely avoidable marks on Xor gate symbol, function, and truth table questions. But after we're done here today, you definitely will not be one of them. We are going to dig directly into what the principal examiner reports say, and I'm going to show you exactly what the marking teams are hunting for when they scan your paper.
Here's our quick roadmap for today's session. We'll start with the challenge, move into the strategy reveal, go through the transformation, hit a quick interactive workshop, and wrap up with the final system and some critical warnings.
All right, Act 1, the challenge. Let's jump straight into it.
Okay, I want to look at a classic past paper scenario that absolutely trips up the vast majority of candidates. To do this, I want to introduce you to our two typical students, Alex and Sam. Now, I want you to think about which one of these sounds more like you, because they perfectly capture the two biggest traps of the computer science exam. Over on the left, we've got Alex. Alex is a hard worker. Alex has spent literally hours memorizing the textbook word for word. So when Alex sees the word Xor on the exam, he panics, but like in a good way, and just overloads the page with raw facts. He writes down the history of logic gates, every single symbol he can possibly think of, but he provides zero actual analysis of the specific circuit diagram sitting right there in the question. The result? 0 marks for application. Ouch. Then, on the right, we have Sam. Sam is incredibly smart, but Sam rushes. Sam skims the question, completely breezes past crucial command words like evaluate or analyze, and just jots down a super basic description. Both of these approaches, they lead straight to a sea of red pen marks and lost grades. Why? Because Cambridge computer science examiners aren't looking for human encyclopedias. Candidates have to demonstrate a connected, conceptual understanding that is completely transferable to unfamiliar contexts, not just spit out raw facts they crammed the night before.
So before we can actually fix Alex and Sam's mistakes, we really need to step back to the absolute basics. Top-performing A-star students always build their conceptual understanding starting with incredibly precise definitions. The entire theoretical architecture of this topic rests on getting this right. So what exactly is an XOR, or exclusive OR gate? Simply put, it is a logic gate that outputs true, or a 1, only when its two inputs are strictly different. If the inputs are exactly the same, it outputs false, or a 0. It is the classic one or the other, but definitely not both, gate. You must have this etched into your brain before you can even begin to apply it to a complex exam scenario. And this truth table perfectly illustrates that exact definition in its absolute purest form. Just look at it. Input A is 0, input B is 0, the output is 0. Input A is 1, input B is 1, the output is 0. They are exactly the same, so the gate just shuts it down. It only gives you that beautiful true 1 output when the inputs are 0 and 1 or 1 and 0. Now, sitting here right now, you might be thinking, well, yeah, this is super easy. But here is the multi-million-dollar question straight from the senior examiners. Why on earth do students find interpreting these binary representations so incredibly hard once they get into the exam room? Well, the answer from the principal examiner reports is that students completely freeze up when these 1s and 0s are placed into completely unfamiliar contexts, like a parity checker or an error detection circuit. They know the basic table, sure, but they have absolutely no idea how to cross-link the topic.
Which brings us to Act 2, the strategy reveal. How do we actually fix this? You need a framework. Without a framework to handle those complex questions, you're just guessing. You need a reliable way to decode the assessment objectives and those really tricky command words. So we use the Peel framework. It's a game changer. Number 1, point. Make your initial statement directly answering the command word. Boom, start strong. Number 2, evidence. Actually pull specific 1s and 0s or logic gates right out of the provided scenario. Number 3, explanation. Detail the causal relationships. Why exactly does this input lead to this output based on the XOR rules we just talked about? And finally, number 4, link. Tie it all the way back to the overall system requirement or context. This right here is the foundational structure that top-tier candidates use to ensure they never, ever write a vague or generic answer. Let's test this out. I want to challenge you right now.
Imagine candidate A writes, the XOR gate outputs 1 because it's a logic gate. And then candidate B writes, the error flag is raised because the XOR gate outputs a 1 since the parity bit and calculated bit are different, meaning data corruption occurred in transmission. Which one of those correctly applies the Peel framework? It's candidate B, for sure. They are actually demonstrating that deeply connected understanding the examiners are begging for. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Let's move into Act 3, the transformation. We are going to fix some answers live.
But wait, before we do the rewrite, you absolutely need to understand the method mark strategy. Honestly, this is a massive secret to lowering your exam anxiety. Cambridge computer science papers actually award marks for the process itself. Think about that. If you're calculating a huge, complex trace table with multiple XOR gates and you make some silly little addition error at the very end, you don't lose all the marks. Earning points for demonstrating the correct logical process is key. This is exactly why you must show your working step by step. How you arrive at the solution matters immensely to the person sitting at a desk grading your paper.
So to secure every single one of those method marks, you need a bulletproof system. Here is the 5-step procedural framework for tackling complex XOR questions, and we pulled this directly from analyzing top-tier exam performances. Step 1. Deconstruct the question. What is the command word actually asking you to do? Step 2. Extract the relevant data. Pull out the specific inputs given in the text. Step 3. Select your analytical framework. Is it going to be a truth table or a trace table? Step 4. Execute with clear notation. Write out that binary clearly so the examiner doesn't have to squint. Step 5. Present with the correct terminology. Please don't say it flips. Say, the XOR gate outputs true due to differing inputs. This procedural framework develops the exact skills needed to prove your practical application.
Okay, let's actually guide you through a live rewrite. Take a good look at this before answer. This is what examiners call vague technical details and generic steps. It says, the XOR gate is used. It makes a 1 if inputs are different. This helps the program run. Yikes. The examiner gives this 0 marks because it is completely 100% divorced from the question's actual context. It's just a generic fact. Now consider the after version where we apply our framework. In the context of the temperature sensor circuit, the XOR gate compares the current reading, input A, with the baseline, input B. Because input A is 1 and input B is 0, it outputs 1, successfully triggering the cooling alarm. Do you see the massive difference there? We replaced generic fluff with context-specific analysis and logical progression. We proved we understand the scenario. And just like that, those red marks turned into green check marks.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Welcome to Act 4, the interactive workshop. It's time to put all this theory into practice. Challenge 1 is a 60-second data scan. Look at this complex XOR logic table representing a system state. You have 2 scenarios here, an error check and a parity check. Scan that data. What is the core trend happening here? Let's break it down. In the error check scenario, both inputs are 1. The XOR output is 0, and the resulting system action is to flag. But in the parity scenario, the inputs are different, 1 and 0, the output is 1 and the action is pass. So what's the core trend you need to extract for your exam answer? It's that the system is utilizing the XOR gate's unique property of detecting differences to validate data integrity. If the inputs match, it flags an error. If they differ, it passes. Being able to quickly extract this kind of core trend from a wall of raw data is exactly what separates the A-star students from everyone else.
Now, moving beyond just reading tables, the exam will often ask you to evaluate the quality of an algorithm that actually uses these logic gates. The critical criteria for evaluating algorithm quality in a Cambridge exam require you to identify 4 specific pillars: time complexity, space complexity, edge cases, and their overall effect on performance. You have to keep these 4 pillars locked in your mind because top-scoring candidates always demonstrate high-level evaluative thinking by analyzing these exact trade-offs and justifying their decisions with hard evidence. Keep these in mind because you're going to need them for this next challenge.
Challenge 2. Find the flaw. Read this extremely flawed statement. The algorithm is fast, but uses memory. Why does an examiner dock marks for this? Because proper comparative analysis requires identifying similarities and differences, using strong comparative connectives, all supported by evidence. That statement is just way too generic. Now consider the perfect answer. Despite higher space complexity due to the additional array, The time complexity improves significantly because the XOR swap logic eliminates the need for a temporary variable. Wow! See how it uses the connective despite, deeply analyzes the specific trade-off, and draws a firm conclusion? That is exactly how you secure maximum evaluation marks.
Challenge 3 is a speed sprint. You have exactly 30 seconds. I want you to mentally draft, or write it down if you're quick enough, one perfect PEL paragraph addressing an XOR edge case. Imagine the exam question asks, what happens if a power surge causes both inputs of the XOR security gate to spike to 1 simultaneously? Go. Seriously, think about your point. Think about your evidence. They're both 1. Explain the causal relationship based on the truth table rules we learned earlier. And finally, link it back to the overall security system failing or locking down because it's receiving identical inputs. If you structured it correctly using PEL, you just proved to yourself that you can handle the absolute toughest edge cases these examiners can throw at you.
Finally, Act 5, the final system, and some critical examiner warnings.
All right, here is your ultimate cheat sheet recap. Take a screenshot if you have to. These are the 3 strict rules that basically guarantee top marks on your Cambridge computer science papers. Rule 1, command word decoding. Never, ever start writing your answer until you know for a fact if you are being asked to state, describe, analyze, or evaluate. Rule 2, PEL framework application. Structure your thoughts. Point, evidence, explanation, link. Never leave your examiner guessing where your logical train is heading. Rule 3, time management matrix. Strictly allocate your time based on the marks available, and always leave yourself enough time to execute that 5-step procedural framework for complex trace tables.
This quote right here from the Principal Examiner Reports is arguably the most crucial takeaway of this entire explainer. Listen closely. Examiner alert. The classic mistake is providing generic answers. Always link every point to the given context. I literally cannot stress this enough. If the exam question is about a washing machine's microchip, your XOR answer must talk about water levels and spin cycles. It cannot just be about binary ones and zeros. Generic answers are the absolute biggest trap students fall into year after year. Context is king.
So to make sure you never fall into that trap, here is the critical timeline of final checks every single student must execute before moving on to the next exam question. Step 1. Check context. Did I actually mention the specific scenario in my answer? Step 2. Verify boundary conditions. Did I test the limits of the inputs provided? Step 3. Test edge cases. As the examiners explicitly noted, students frequently forget to check boundary conditions and edge cases. Ask yourself, what happens at the absolute extremes of this data? If you run your logic through this timeline every single time, your answers will be absolutely bulletproof.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
We really want to hear from you. Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Is it breaking down those trace tables? Is it algorithmic evaluation? Let us know. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep practicing, keep applying that PEL framework, and we will catch you in the next explainer.